Now, when it comes to researching, we do something we call operational research, and then we do resource allocation. So if we have data, that tells us that, okay, we are going for data collection, we are going to do data analysis or data collection, and we have a population. Because we've done several or similar research works on this, we know that this particular part of the country or this particular part of the region, they have higher population. So we need to send in more research assistants there. We need to send in more facilities there so that it can accommodate them. And all this is as a result of the data analysis. Then we also have preventive care. Now, preventive care is a very interesting field, which is now currently growing in all medical facets or health facets. Because it's better you prevent than to wait for the person to get the health outcome than you now treat. So it's now on a rise. People are paying more attention to preventive care. And we can easily help improve preventive care with our robust data analysis or statistical or machine learning models. Because this helps us in identifying high-risk patients, and then it can help in early detection or early intervention to prevent the disease from happening. And it is more typical of chronic diseases. Then overall, we have improved patient engagement. With this one, currently at the Kumasi Center for Collaborative Research in Tropical Medicine, we are currently developing an AI model. So we are developing the AI model to act more like a personal doctor, health doctor. And this has been enrolled. We are still at the initial stages. We are testing it. And how it works is that you keep communicating with it with your health problems. Let's say chat, it's more like chat GPT, but it's like a personalized chatbot. So you keep emailing or you keep messaging it. Oh, good morning, this, I'm experiencing that, I'm experiencing that. Then through that, it is able to keep your medical history to ask you for some specific questions. If you've ever done this, you've ever gone to this, you've ever had this, then it accumulates all the medical history. Then it gives you first aid techniques first before it now recommends you to the nearest, it connects you to the nearest hospital that is available for you to go for treatment. So currently that is the model we are building on. Now, we are now coming to the main presentation for today, and these are the objectives of our presentation. Look at statistical modeling, introduction to Python, and then the tool for analysis. We look at the machine learning applications, then also look at some few real-world examples in health research. Now, before we do any statistical analysis, before you go into any statistical analysis, then you have to ask who will be your users. Are those using the analysis or those you are analyzing the data for, are they clinicians, policymakers, researchers, program managers? Then what insight do we want to our users to gain from the data analysis? Are we looking at trend analysis, predictions, risk factors, comparative analysis? Then is this the best way to present the data? Because sometimes data that is supposed to be presented in graphs, people present in tables. Data that you are supposed to present in tables, people present in graphs, in dashboards, and then in predictive models. So you need to understand your data, know your people, know the tools you are using, and then how to present the data to them. Then the fourth one, do the data quality also, do the data actually support the analysis we want to do? In this regard, we look at the data quality. If we have a redundant data, then our analysis is going to be something that is not reliable. And then when it comes to research, we are more focused on reliability and then validity of the analysis. So if the data quality is lacking, if the results is not reliable, it is not valid, and then you cannot do any generalizability of the results or the research or the data analysis. They will look at missing values, sample size, assumptions, and then variable types. So before you pick any statistical software or sorry, any statistical model or analytical tool, you need to look at the assumptions of that. Every model has an assumption it must follow. And then you look at the outcome variable, whether it is continuous, is binary, is count data. Then you also look at whether is the data normally distributed, is it skewed? All these are assumptions that you have to put into consideration or put them in place before you start any data analysis. Now, statistical analysis or statistical modeling in health data. So this basically has to do the methods of data collection, classification, summarization, interpretation of data, and then this is done to draw inference and then test your hypothesis. And when tools of statistics are applied to data derived from biological sciences, such as medicine, it is known as biostatistics. So a biostatistician is someone who applies the tools of statistics to medical data to draw insights or to uncover trends. Now, the common methods that we know are mostly linear regression or regression models. We have logistic regression, survival analysis, Cox regression, Bayesian regression, descriptive statistics, that is the mean, the median. Then we also have the comparative test, that is the t-test, the ANOVA, chi-square, and then Kruskal-Wallis, and then all those are the comparative tests. Now look at the common statistical models in health. Now, when you take any statistical model, just as I mentioned before, you need to look at certain assumptions of it. And then one of the key assumptions is for you to check the outcome variable of it. And an outcome variable is more like the dependent variable or the response variable, or some say the Y variable. So look at the assumptions, look at the outcome variable. Now let's look at linear regression. We know that for linear regression, it is trying to establish a relationship between two or more continuous variables. So for linear regression, if you are doing analysis involving linear regression, you must make sure that your outcome variable, the variable that you are so interested in, the Y variable, it should be a continuous variable. Example, weights, heights, laboratory values. And then we say continuous variables, they are count variables, or they assume measured variables. Now, typical research question we can ask is, how does X affect Y? In the sense that does a unit increase in X cause Y to increase or decrease? So that's the type of relationship we are trying to establish. When X increases, is it going to affect an increase, or is it going to change the increase or the change in Y? And then typical example is predicting blood glucose level, BMI, and then diet. Now, we also have logistic regression. So logistic regression here, our outcome variable, we are more focused on it being a binary variable in the sense that it is either a yes or no answer or a 0 or 1. That is for the binary. And this one models the log odds of an event occurring. The log odds of what events occurring. Then Poisson regression, the outcome variable here is a count data. That is events per unit time. And this models the log rate. So for Poisson regressions, for instance, if I try to model or try to look at the number of calls coming in at particular intervals at the hospital, what I'm doing is Poisson regression or Poisson data analysis. At each particular point in time, the calls coming in, I pick out that count data, time 1, time 2, time 3, time 4, and I try to model it. That is Poisson regression. Now, negative binomial is an extension of the Poisson regression. One of the assumptions or one of the factors that affects the generalizability of Poisson regression is is zero inflated means and then over dispersion. Now, when over dispersion happens, or you are having a lot of zeros in your data, we call them zero inflated means, then we now extend the Poisson regression to something we call negative binomial regression, Well, your focus now will be on what? Modeling the over-dispersed count data. A typical example is modeling malaria cases in districts with high variability. So high variability here shows that there's a lot of over-dispersion. So I have to take my time to model the over-dispersed count data and not just the mere count data. Another interesting concept or another interesting statistical model that is widely used in health, especially in cancer, is survival analysis, particularly Cox regression or Cox proportional hazards. And survival analysis is an analysis done time to death or time to event analysis. So if I'm following cancer patients to see when the patient dies or when the patient develops more complications, then what I'm doing is what? Survival analysis. For survival here, we are interested in the time to death, time to failure. That is our events of interest or ICU readmission. Now, a concept that has not been so common, but then it is very flexible to use is what we call as the generalized linear models, GLM. So the GLM is an extension of the linear regression. Sometimes if you have your data and then you want to go more like you want to achieve flexibility in your analysis, you can, for the linear regression, it's only limits you to continuous data. But when it comes to the generalized linear models, you can do continuous, so it's probability distributions. So you can do Poisson, you can do logistic, you can do the other counts as well. Some think it's difficult, but it's when it comes to modeling historical health data. I said historical health data because Bayesian regression, what it does is that it models the data based on prior distributions available. So it takes prior information on the data it has, then it models the current data. So that's what Bayesian regression does. And Bayesian regression too can be applied to any outcome, be it continuous, binary, or count. And then last model of the ARIMA, we have MA, that is movie. These models are normally used for longitudinal data analysis. Longitudinal data analysis are continuous data that is also collected over time. And then we're also trying to see if we can predict because most of the predictive analysis, we use time series analysis because it also collects historical data. So if we know that, okay, in this particular region we have a lot of people who have been or reporting or these cases over the few years, we can take what has been happening over the few years, then we incorporate it into our model, then try to predict what might happen in the next 2, 3, or 4 years. Now let's look at a case study with one of the models. So a researcher wants to describe the relationship between systolic blood pressure and an age in a group of teenagers and young adults in a rural population. So the researcher here is interested in describing the effect that age has on systolic blood pressure. Now, this was an output from Stata. This can be done in R, it can be done in Python, but this is an output from Stata. Now, when you run this particular, the data we used over there was data from a survey that was conducted in one of the rural villages in Ghana. So we ran the regression model. This was a basic regression model, that is linear regression model. And then in the model, this was the outputs we had. So if you look at the outputs, you're going to see that we have output from data, then we have source, we have another table down there with the systolic, then we have number of observations. Now, these are three different components of the results, and then these are all important. The first part you see is called the ANOVA table, the one containing the source, the SS, the DF, the MS, model residual. We call it the ANOVA table. Now, underneath it, we have a long table that starts with six coefficient standard error t p greater than absolute value of t. That table is called the parameter estimation table. Parameter estimation table in the sense that it houses or it contains the variables that you are using in your regression model. That's the regression parameters. And then at the far right corner, we have a third table that has number of observations. Number of observations, it has the F distribution, then it has the probability greater than F, then it also has the R squared. So this particular table, we call it the overall model fitness. It is called the overall model fitness table. And then that is what's used to tell whether your model is fit enough to be generalized. Okay. So now, if I'm going to focus more on the parameter estimation and then the overall model. So when you have an output like this and you check at the overall model to see if your model can be generalized, look at the p-value, that's the probability greater than f. So here we see that the probability greater than f is 0.000, which is significant. So if your p-value is significant, then it is telling you that at least one of the independent variables, that is the x variables, can reliably predict the outcome variable. So at least it is telling you that at least age can reliably predict systolic blood pressure. So we are hoping that if that is the case, if this model is thrown into any hospital at all, then it should work. Because if it is reliable predicting it, that means it has been standardized. Okay. Now, when you come to the parameter estimation, we have cis, then we have underneath we have age, and then we have the constant. You also have the coefficients. So here the coefficient of the age is 0.631 and the constant is 98.3. We also have the standard deviation. We have the p-value. Now we look at the p-value of the independent variable age. So the p-value of age is 0.000, which is significant. So it is telling us that age here is statistically significant in predicting systolic blood pressure. Similarly, if you look at the constant is significant. Now, your regression model is written as y, which is the outcome variable. In here is going to be systolic blood pressure. It's equal to your B naught, that is the beta naught. Beta naught here is our constant, which represents the 98.3 plus beta 1 x. And the beta 1 here is the coefficient of the independent variable age. So here our beta 1 is 0.631. So now, once we have our betas and we have um, our independent variable, we can construct a model. And our model here is systolic blood pressure, or BP, or SIS, is equal to 98.3 plus 0.631 of age. Now, this is basically telling us that averagely, averagely, an individual, for an individual presenting systolic blood pressure at uh, the age, sorry, at the hospital, a unit increase in age of that individual would cause systolic blood pressure to increase by 0 because the age variable here is significant. So this model is a reliable model. Now, we move to our next section. Now, why Python? I remember when I was first introduced to Python, I was thinking, Python, what kind of name is that? And there's an interface to call Anaconda. So I was like Python, Anaconda. Those names were not something that's in Africa. If you say Python for the first time, people just think it's the snake and everything. But hopefully, with time, I think I've started enjoying Python more and then working with the Anaconda interface as well. Now, why Python? So Python, one of the reasons why people like using Python because Python is simple. They tell you that Python is very, very simple. Sorry. Python is simple, high level. If you compare Python to more other tools like R is statistically comprehensive. You need to have robust knowledge in statistics before you can transition more into R. But Python is very simple and it's very user friendly. So a lot of people like to learn Python, then later on they transition into R. But either ways, you're gonna be fine because both are just similar things. Now, Python comes with a lot of libraries, and then these are the popular libraries. We have the pandas, we have the NumPy, we have the matplotlib, that's Seaborn, then we have the um scikit-learn, and then the pandas help in data cleaning, data manipulation, data wrangling, and data cleaning is something which are going to suffer. But once your data is clean, you're going to have a very smooth analysis. They also have NumPy. NumPy is mostly used in numerical computations. Something like if you are doing Gaussian regression, some you are doing Gaussian analysis, numerical analysis, Nielsen-Raphson methods, iterative methods, you have to bring NumPy in because it helps in numerical computing. Then Matplotlib or Seaborn helps in the visualization aspects of Python. Then we have scikit-learn. That is where it helps or it eases machine learning models or the use of machine learning models for you. And we are going to be using them in the training sessions with time. Yeah. So hopefully this is more like a Python extracts which I used for mathematical modeling some time ago. Yeah. So now from raw data to insights. So this was a data collected on neonatal mortality somewhere 2023. Now we collected data on neonatal deaths and then on mortality rates. And then this is an aggregated data from DIMS. So this is an aggregated data from DIMS. And with this data, I was trying to see if I could actually forecast the data. But first of all, before I do any forecast, I have to first understand the current trends of the data. So I was trying to see if I could see what the data represents currently and then how the trends could be seen into the future, somewhere like 2030 or maybe 2035. So collected this data, then this is just the code I used. And these were the two insights or the two graphs that were gotten from the data. Now, the first one, if you look at the neonatal deaths, see there's a huge drop from 4,000 to somewhere around 1,005. Yeah, somewhere around 1,005 in 2017. Right, from 2016 to 2017, there was a huge drop. Now, the lowest points of neonatal deaths that were observed in Ghana from 2016 to 2024 was somewhere 2018, and then that was 1,000 deaths. But then it started rising again from 2018 to 19. And then within that period, we had more like 1,002 to 1,007 deaths in total. Then slightly came down, then started rising again. Then it dropped again. Then
I don't know why they got
currently it's on a rise
target
again.
better.
Now, when you have this, you see there's a rise and fall, rise and fall, rise and fall. That is the visualization. So if we had the figures, let me go back to the previous slide. In the previous slide, we had figures this way. I couldn't just look at the figures and I'll say that okay, it's okay, it's bad, it's okay, it's bad. Because the figures wouldn't be able to give you that visual component of it that you can use your eye to see. But now when you try to visualize it, and then the line is there, the pattern is there, you can see how, should I say, dangerous it is. But for the figures will just tell you that, oh, this year we had this 1,000, the next year 2,000. You see the severity of the cases. But when you plot it, that's when you see the severity of whatever issue that we are facing over there. So that was what we did. Now, the first question when we presented this data, the first question they asked us was that why was there a drop? The drop was fine, but then it was a sharp one, dropping from 4,000 to somewhere 1,005. What happened? What could have caused the drop? So those
But
are the
let me
questions they
finish.
ask. So when you present it this way, you see now people look at it and they ask, okay, so there was a drop. What caused the drop? And then there was a further drop. What caused it again? Now, in 2020, we had like 1,000. Why couldn't we maintain? Sorry, in 2018, we had 1,000 deaths. Why couldn't we maintain the deaths again and then it rose again? And these are the questions they ask from insights when they are drawn. Eh, Now, now to the other far right corner, we look at the institutional mortality. At the various institutions, we look at it in every region, how mortality rates were handled, the drops that were observed, and then everything. So from here, 2016 to somewhere 2017 to, we can see that there was a very steep rise. And this will bring questions on board. They'll ask you, oh, well, we can see there's a steep rise. Why that? And then you have to provide insights or you have to provide reasons for that. And then these are based not only on the part of the data analyst, but then we have policy implementers, we have other stakeholders that we bring onto board. That's why the research team is more like a collaborative team. It's not a one-man job because there's supposed to be someone doing the insights, and then there's supposed to be other people, more like health economists, and then other managers, other stakeholders who put more insights into the plots that have been made. So here we've moved from data to insights. Here we had data. Now the charts has given us more insights into the data that we have. Now, this was where the forecasting happened. So for the forecasting, what I did was that I tried to use a time series model. That is the ARIMA model, the auto-regressive moving average model. That was what I used. And in this model, I was trying to see if it was possible for me to predict into the future, somewhere 2030, to see how the mortality or the neonatal mortality trends will be looking in Ghana. Is it going to be decreasing or is it going to be increasing? Or is it going to be moderate? And what are the early interventions that we can bring onto board to curb this from happening? So if you look at the first model, there's a blue line. We have two blue. We have a light one and then they see blue. And then within it is a line. So the band over there you see around the line, that band tells you or it shows you the confidence interval. And then the standard confidence interval we use over there is 95% confidence interval. Unless, of course, you want to change your confidence interval. So in the time series analysis, the plot over there shows a declining trend in neonatal mortality. That is from 2020 to through to 2024. And then it drops from peak 8 to peak 5. Okay. Now, if you look at the forecast model over there, the bands they widen as we moved further into the future. The bands widen as we move further into the future. That is the confidence interval over there. the bands, they were wide as we moved into the confidence, sorry, into the future. Now, there are two things we have to take note here. When you are doing any predictive analysis, you have to take into account your time bounds. Because if your time bound is narrow, it gives you more confidence. It provides more confidence within the model because it brings this certainty. But when your band is wide, it brings more uncertainty. That means you are creating room for more factors to come into your prediction or your predictive analysis. Okay. Yeah. So this is a clear example of forecasting. This was done with ARIMA model, one of the statistical tools in its time series analysis.
Yeah, sorry,
Now
Mr.
to machine.
Osman, sorry to interrupt you. Just because of time, if you can, like, kind of hasten up, or maybe 5 minutes or so. Thank you. It's
Oh,
10 minutes.
oh, sure, sure, sure. Okay, sure. So, for machine learning models, it's, shall I say, a subset of artificial intelligence, and we've all heard about artificial intelligence, AI, AI, AI. AI is about challenges. Then these are the reasons why AI matters because it helps to get insight from complex data. Sometimes when you have large data sets, you wouldn't be able to use these our I don't want to call them weak, but then they are more like smooth data analytics tools. So you go into a highly advanced computational tools such as machine learning to do that for you. So if you look at the machine learning world, we have from AI to machine learning, from neural networks, and then to deep learning. And then after AI, that is artificial intelligence, the next subset is machine learning, where machine learning we just focus on structured labeled data to make predictions. Then to deep learning. And then one component between the machine learning and the deep learning is the neural networks. So just like the brain. So neural networks are more like brain-inspired models that we use to automatically detect features and relationships. And that's what we use in image recognition. Okay. Then the deep learning part of machine learning is like the experience part of it, just like a human being. When you are giving birth, till the time you are right now, you've gained a lot of experience, and that's how deep learning works. So deep learning works from experience of the instructions, the prompts that it has been getting. So it learns, and then it learns from the experience to do things better next time when asked to do similar stuff. So now for the machine learning, we have we have three main types, but then of recent, some people have tried to blend um some people have tried to blend supervised and then unsupervised models to see if they can come out with or other techniques. So with the supervised learning, what we do is that we use labeled data set to train algorithms to classify or predict outcomes. And then the most common ones we have are the classification models, that is the yes or no models, and we also have the regression model. Then we also have unsupervised learning, where we use machine learning algorithms to analyze and then cluster unlabeled data sets. And then the most popular techniques over there will be classroom models, dimensionality reduction. And then dimensionality reduction is used to prevent over dispersion, over underestimation of um, data when you are doing data analysis, especially in Poisson data analysis. Then we also have the semi-supervised learning, which is a mix of the labeled and unlabeled. Then reinforcement learning, which can be described as learn by doing through a series of trial and then error experiments. So this is the data, machine learning data or workflow. You collect your data, you clean your transform your data, then model selection, you train your data or you train your model, you test your model, then you evaluate the model, then you deploy the model for inference, and then the prediction of models from machines to do spatial analysis.